Hello, this will be a demonstration of proposition 30 from book 6 of Euclid's Elements, which requires us to cut a given finite straight line into extreme and mean ratio. Now, if you don't remember what extreme and mean ratio means, this is described in the third definition of book 6, that's definition 6.3. A straight line is said to be cut in extreme and mean ratio when the whole is to the greater segment, just as that greater segment is to the lesser segment. What we're given to accomplish this proposition is some finite straight line AB, and this is all we're given, and the task at hand for us is to cut this into extreme and mean ratio. We're going to begin by describing the square on AB, and we're going to call it BC. We can do this by proposition 146. So we're just going to call it by its diagonal, BC. Next, to AC, we are going to apply the parallelogram CD, which is equal to BC and exceeds the straight line CA by the parallelogram AD, which is similar to the square BC. This is proposition 623, or not 623, 629 is the prop right before this one. Where we figure out how to accomplish such a construction. And all that's going to look like is we're going to have something like this. Like this. So this parallelogram CD is going to be equal to the whole square BC. And this excess parallelogram AD is going to be similar to the whole square BC. And we're going to say that this straight line here from D cuts AB at the point E, and it goes up to this side of the square to point F. Okay, now we have everything that we need, and I'm going to prove that this straight line AB is cut into extreme and mean ratio at this point right here, this point E. It has been cut into extreme and mean ratio. First, because BC is a square and AD is similar to BC, it naturally follows that this parallelogram AD is also a square. You can do this by appealing to the definition of a square, which is definition 122, along with proposition 514. I'm not going to go through it. Euclid doesn't go through it, and it's trivially easy to do. But all that matters is that this parallelogram AD is a square. Now, because the square BC is equal to the parallelogram CD, we had made it so. If we subtract this parallelogram CE from both, well, by combination 3, we'll get equal remainders, so that the remaining parallelogram BF is equal to the remaining parallelogram AD. So again, BC is equal to CD. We subtract CE from both. That leaves us with the parallelogram BF being equal to the parallelogram AD, or the square AD. Now, because the angle FEB is equal to the angle AED, by proposition 115, these two angles FEB and AED are vertical angles, so they are equal to each other. And furthermore, we have just shown that the parallelogram BF is equal to the square AD by proposition 614, that if you have equal parallelograms, which have one angle equal to one angle, the sides about the equal angle will be reciprocally proportional. And what that's going to look like here is that FE is to ED, just as AE is to EB. Now, I discussed in that video 614 as well as 615 how exactly to know what reciprocal proportionality is, or how to detect it when you're given it. And I had said in that video that you can make note of reciprocal proportionality when the two terms here, the two mean terms, are from the same figure. And here this proportion satisfies this. ED and AE, these two straight lines, are both from the same figure, so this is reciprocal proportionality. So FE is to ED just as AE is to EB. Now, we know that the straight line here, FE, is equal to the straight line AB. We know this because FE is equal to CA right there, right? Because CE is a parallelogram. So 134 tells us that the opposite sides in a parallelogram are equal. So AC is equal to FE. But we also know that AC is equal to AB. They're both sides of the same square, which means definition 122, that is the definition of a square, tells us that these two straight lines are equal, so AC is equal to AB. But FE is also equal to AC, which means we have two things which are equal to the same thing, common notion 1. These two things are equal to one another, so that FE is equal to AB. And more simply, we know that ED is equal to AE. We know this because we had shown that the parallelogram AD is a square, and so by definition 122, it's equilateral, so the straight line AE is equal to the straight line ED, which means we can substitute these into our proportion here by a property of magnitudes to say that AB is to AE just as AE is to EB. Now, we know that AB is greater than AE by common notion 5, right? AE is a part of AB and the whole is always greater than the part, so AB is greater than AE, which means by VI.30, if a first magnitude is to a second, just as a third is to a fourth, and if the first be greater than the third, then the second will also be greater than the fourth. So because the first AB is greater than the third AE, the second AE must be greater than the fourth EB, which means that this straight line AB is cut into extreme and mean ratio at E, because the whole AB is to the greater segment, which is AE, just as the greater segment AE is to the lesser segment EB, which means we've done that which we set out to do. The given straight line AB has been cut into extreme and mean ratio at the point E, Q, E, F. Now, I love this prop, don't get me wrong, this is an amazing prop, I'm a big fan of extreme and mean ratio, but there is admittedly a simpler way to accomplish this proposition that takes 2 steps at most. You can do this by taking the straight line AB and cutting it at some point C such that the rectangle AB times CB is equal to the square AC. We can do this by proposition 211. That was the proposition where we learned how to cut a straight line such that the rectangle contained by the whole in the lesser segment is equal to the square on the greater segment. So if we cut the straight line AB at point C such that AB times CB is equal to AC squared, then by proposition 617, which tells us that if a rectangle contained by 2 straight lines be equal to a square on a third straight line, the 3 straight lines will be proportional. Namely, that the sides which contain the rectangle will be the extremes, and the side of the square will be the mean. So if we cut the straight line AB at the point C, such that AB times CB is equal to AC squared, we can then say by 617 that AB is to AC just as AC is to CB. And thus, AB will have been cut into extreme and mean ratio at the point C, because the whole AB will be to the greater segment AC, just as the greater segment AC is to the lesser segment CB. So that's an alternate way to do this proposition. You might be able to figure that out just from how similar these diagrams are. If you go back to my 211 video or simply look at both of the propositions up and compare the diagrams, they look basically identical. You take the straight line, you put a square on it, you have another rectangle like this, and this little bit coming out is a square. 211 has a few more straight lines because in that book, Euclid did not have a theory of proportionality or similarity, so there's some easier things we can do in this prop that we couldn't do in book 2, but nonetheless, they are the same prop. Cutting a straight line such that the whole segment times the lesser is equal to the square on the greater is the same thing as cutting a straight line into extreme and mean ratio. That's by proposition 617. Now, the last thing that remains for us to talk about with this proposition is just a general note about extreme and mean ratio, because nowadays you will not hear this called extreme mean ratio unless you're studying Euclid. You'll often hear this called the golden ratio, which has kind of been popularized into this weird mythicism. It's all a bunch of hat garbage, but the golden ratio is a very real mathematical concept. And it is the same thing as extreme mean ratio, that a straight line is said to be cut into a golden ratio when the whole is to the greater segment, just as the greater segment is to the lesser segment. Now, there's a famous number that we can figure out with the extreme and mean ratio, or the golden ratio, whichever name you want to call it by. We can do this by virtue of quadratics. So if I say that the greater segment, we're just going to call that length 1. It doesn't really matter how long it is, I'm just going to call it length 1 to make the calculation simpler. Then we'll be able to say that the whole straight line, which I'm not going to call AB, I'm actually just going to call it by the Greek letter phi, because this is the symbol used for the number we're about to find, that phi, which is the whole straight line, however long the straight line, we'll say its length phi, is to the greater segment, which I'm just going to say is 1, just as the greater segment 1 is to the lesser segment. Well, the lesser segment is just the whole segment, or the whole straight line, minus the greater segment. So the lesser segment we can represent by phi minus 1, so that this straight line AB will satisfy the ratio such that phi is to 1, just as 1 is to phi minus 1. Now we can solve this first by cross multiplying. We can do that by proposition 16, of course. So we can cross multiply and say that phi squared minus phi equals 1. And we can say that phi squared minus phi minus 1 equals 0, which means we have an equation that we can just solve with the quadratic formula. And if we use the quadratic formula, we find out that phi is equal to 1 plus or minus root 5 over 2. Now, because we're dealing with actual straight lines, and the square root of 5 is greater than 1, what would happen here if we use the minus sign, we would end up with a negative length, which is obviously absurd. So we often just say that phi is the plus sign, so that phi, the length of the whole straight line, if the greater segment is 1, then the length of the whole straight line will be 1 plus root 5 over 2, which if you work that out, comes out to be 1.6180339, 88749894, 848204, 5868. I might be wrong about those last 10 digits, but it's roughly 1.618, which is one of those really famous mathematical constants up there with pi and e and root 2. So you ought to know it. It's quite a cool constant, and a lot of neat things come out of it, particularly to do with pentagons that we'll see a lot of in book 13, frankly. But yeah, so that's all I wanted to say about this proposition. A full demonstration of 630, an easier way to accomplish the construction, and solving for the golden ratio, which we've found to be 1.618, and this is represented by the Greek letter phi. Now, I've got nothing else to say about this proposition, so I'll end the video here and move on to 631.